On this beautiful day in advanced algebra and trigonometry, we're going to talk about the language of functions. So our goal for today is we're going to give definitions, we're going to talk about properties, and how to represent functions. So first off, by warm-up, you determined whether the relation down here in this graph or over here in this table is a function. Explain if you can, and then list the domain and range here. This first one is a function. Yes, this one is a function. And over here is not a function. Now, of course, the real reason is why. Tell me why. So let's look over here of why number 2 is not a function. Notice that number 1, that a 1 right here, it maps to a negative 2. But then a moment later, we see a 1 again, and it maps this time to a 3. If we were to do a mapping diagram with just a few numbers right here, we would see that the 1 maps to 2 different numbers, a negative 2 and a 3. And we would see that the negative 1 only maps to a 2, and the negative 2 only maps to a 4. Because of this split right here, because the 1 is inconsistent, you input a 1 and out pops a negative 2. You input a 1 and out pops a 3. It's inconsistent. In other words, it's not trustworthy. We don't know. It's hard to determine. It's just inconsistent there. So this one is a function. And do we recollect why? Yeah. Vertical line test. I'm going to abbreviate it with VLT. And the vertical line test is hard to describe with words. It's easier to describe like this. If you're looking at vertical lines, notice it only intersects, no matter which vertical line and however many I draw in between, the vertical line only intersects the function once at any given time. Or over here, technically zero times. So it can intersect not, or it can intersect one time, but in a situation, if this were my function like this, if it curved back on itself, then we would say, oh, look, it intersects more than once, so that would be not a function. Good, so the vertical line test is something we can take a gander at. We've got a bunch of vocabulary. Hopefully this is all review for you. And we're going to chat real quick about what each one is. First off, mathematical term is a relation. In English, a relation is just like your cousin or Rabbit and all his relations, Winnie the Pooh. But a relation really is just any set of ordered pairs. Remember, an ordered pair is an X and a Y. So it could just be a 1 and a 3, and that's it. There's a relation. It could be 16 sets. It could be a line that can be represented by a line, and then you can pull out all the points there. But the ordered pairs are essentially what define it. So some X is being mapped to some Y. There we go. It's just a relation is that. An independent variable is usually the first component. In this case, we're going to say X, but it doesn't have to be, it can be any letter, but generally we say X. And then the dependent is going to be the second component, and we're going to say Y in this case. Now, independent and dependent, that's if the second component is dependent on the first one. So for example, if you're buying clothes, if some shirts, right? And the shirts are like $10 each, right? The cost of the shirts, the cost is dependent on how many shirts I buy. The cost is dependent on how many shirts I buy. So the independent variable is the number of shirts, and the dependent variable is the cost, my total bill. Okay. All right. So what is a function? A function is a relation. A function is a relation, but it's a more specific type. So a function is a set of ordered pairs. That's what it means to be a relation. However, here's the key. In which each first component x is paired with exactly one second component. So here we have an example right here. The f is an example and g is a non-example. In other words, an example of a not function. All right, so this one right here. If you were to map things out, doing a mapping diagram, the 1 maps to a 2, and then the 2 maps to a 4, like in this case right here, and then here the 3 maps to a 7. Notice that it's consistent. Every single time I see a 1, which is exactly once, I get a 2. Every time I see a 2, I get a 4. And every time I see a 3, I get a 7. Okay, so that is a function. It's good to go. This one is not a function. Not a function. All right, so let's see here. In the first case, just to clear it up, here, the 1 and the 1 there map to separate things. First, it maps to a 2 right there, and then it maps to a 7 right there. So that's inconsistent, so it's not a function. It doesn't matter that 1 shows up more than once. That's not the important part. The important part is that it goes to somewhere else. Because you might see, if I erase this and put a 2 right there, oh, look, the 1 shows up more than once. Yeah, that's okay. It does. But it also maps to a 2 both times. So the change I just made here is a function. This piece of data just shows up more than once. That's all. And that can happen in life. All right. So now we get to domain and range. The domain are all the x values or all the independent values. All independent, spell that right, dependent values. So for the f, the domain of f is this. We're going to use a bracket like this. Always use a bracket. And all we're going to do is list all the x values that are there. And I'm doing this specifically for x. So the 1, the 2, and the 3. Please make sure that you list them in order. If they're not in order up here, if it starts with a 2, make sure you just go and start with the lowest number there. So the 1, a 2, and a 3. And it ends. There's no, it's discrete. There's just 1, 2, and 3, nothing more, nothing less. All right. Now the range is all the dependent values. And let's look at the ones specifically of x. Again, we use a bracket. In this case, it's just going to be the 2, the 4, and the 7. Again, I'm going to write this not in the order that it's written, but in the order of from lowest to highest. So a 2, a 4, and a 7. It's just coincidental that it happens to be already in order. So we can have a domain and a range of a function. Turns out you can have a domain and range of a non-function too. So we can do domain and range over here. So what would be the domain and the range of these? Go ahead and tell your neighbor. What's the domain and range of these? The domain is just 1 and 2 of this relation. Notice that although 1 shows up again, we don't have to write it again. And we wouldn't write it in this order 2, 1. We're going to start with the lowest here. The range here is also 2, 4, and 7. And again, all we did was grab the y values right there, and that's from the original one, not the one I changed. So you can have domain and range of any relations or functions. We usually don't talk about relations too much. Relations are secondary. We're more interested in functions. Hence, the name of the course historically has been Functions, Stats, and Trig. So we talk about functions for the most part. All right, a real function. It's not a pretend function as opposed to a pretend function. A real function is simply this. Any function whose domain is the set of all real numbers. most of the functions we deal with are real functions. So just to give a quick example of it, if you had a line that just went like this, and then we draw our arrows right there, the domain are just all the x values. So if we think about what the x values are, this x value counts, this x value counts, this s value counts, this x value, and because there's a line, means that there's an infinite number of points here. So that means the domain is going to be everything on this x-axis, everything, because this arrow goes forever to the right. So that means the domain goes forever to the right. There aren't any gaps. Notice there's no gaps on this line here. I've connected the dots all entirely. And it goes forever to the left, which means my domain goes forever to the left. So how we would write that is fairly simple. We would just say the domain, colon, and you can just use this super secret symbol right here. It's an R with an extra leg. It's just an R with an extra leg, and it means all real numbers. I have a little chart over here from the textbook that gives you other numbers that you can use. If you're talking about just the integers, -6, -5, -4, 5, 4, 3, 2, 1, etc., those ones, you would write it like this. It's like Z with an extra inside like that. That's how you could draw that. Real numbers, I just draw it with two legs like that, and then make my R like so. Q, the rational numbers. Remember, rational is another way of saying anything that can be written as a fraction, so fractional numbers. 2/3, 1.7, anything like that would be a rational number. And this is how I would draw that if we ever needed to use it, is just put an extra vertical line through the Q there. And natural would look just like the integers, just with a second middle part there. The natural numbers are just our fingers and above, right? So 1, 2, 3, 4. That's what the natural numbers are. On example number 1 here, a baker charges $2 per muffin. Customers get a $2 discount for every 6 muffins purchased. In other words, buy 5, get 1 free, right? Which statement is true? The cost, C, is a function of the number of M muffins, or the number of M muffins is a function of cost, C. So, in this case here, you're right that the number of muffins, this is the independent variable, which means the cost, how much I pay, is going to be the dependent. How much I pay depends on the number of muffins I buy. So the answer for below is the cost C is a function of the number of muffins. And you can write it like this. The cost, and I'm going to use a capital C, oftentimes capital C is used for cost, is equal to the function of, and let me put M in there, for the number of muffins. Oh, actually they had a lowercase c there. Since it's already lowercase, let me go ahead and be consistent. And there we go. So the number of muffins is independent, so it goes into the function, and then the cost comes out like that. All right, well, that actually answers our B. B and A are very intricately linked, so we already know which one's independent. The independent was the M, and the dependent was the cost there. And the domain and range of the function. So the domain here, practically speaking, I would walk in and I would not buy 0, right? I mean, if a transaction happens, it's not going to be with a 0. So it would be something like with a 1, a 2, a 3, and a 4. So how to say that would be my natural numbers. The domain is my natural numbers. No negatives, because I'm not selling them muffins. As the customer, that's not what I'm doing. All right, output. What kinds of numbers will come out? And again, my range here is also the natural numbers. More specifically, it's a subset of the natural numbers. It's probably even numbers. However, what's something that this isn't accounting for? Generally speaking? Okay, we got discounts in there, which would actually still probably be a natural number. But what is almost always you're going to have to pay? You're going to have to pay tax, right? So as the scenario is, with the scenario, we're right. This is the scenario. But it would probably be wise up here if it says no tax, right? Or tax is already included, something like that. Down here, though, most logically, it would end up being Q here, because I would probably have decimals, and decimals can be rewritten as fractions. So most likely with that. All right, your turn. Attack number 2 with your neighbor. Go. All right, looking at this example, the Sudoku Club at a high school needs T-shirts for their upcoming tournament. They were able to negotiate a buy 2, get 1 free. Oh, sorry. Buy 2, get 1 free. From a local store. The cost for 1 shirt is $10. Which statement is true? The cost is a function of the number of shirts, or the number of shirts is a function of the cost? What'd you guys come up with, Jekyll? Notice that if we change the scenario a bit, if I were buying T-shirts, notice I can only buy T-shirts in whole increments. 1 T-shirt, 2 T-shirts, 3 T-shirts, etc. If this were pounds of turkey, something like that, I'm going to buy a turkey and it's going to be $7.99 a pound. In that case, can you buy a fraction of a pound? Yeah. Yep, I can. In fact, I could buy 1.7332, depending on how accurate the scale is. So it's not just any old numbers, it's like all the numbers that are in between, really. So the domain and range in a pound question would be a little bit different than something that's incrementally purchased, one thing at a time. All right, what'd you come up here with the independent and the dependent variables, Zach?
The independent is the shirts, and the dependent is
Domain or range, please tell me what you came up with here, Adam.
Domain is natural numbers and range is natural numbers.
There we go. All right, I'm going to pause for a second right there.